Everyone, thanks for your patience. We finally got it working. So welcome to the review session. And does this work?
Is it recording?
It's recording, yeah. Do you want to make sure it's recording the entire time? Yeah. Cool, this works. It has a laser pointer. So this is the exam format. It'll be similar to last time, open book and open notes. You can use a non-programmable calculator, although you shouldn't have to use one. None of the problems require a calculator to be solved. And this time, especially if you want to ask for a regrade on any true, false, or multiple choice problems, please answer them in blue or black pen. So it's easier for us to know like which one you actually intended to circle. And don't use red pen at all. One person did that, and we were joking about failing them because we couldn't grade it. But yeah, don't use red pen. Yeah, we'll still grade it, but we'll just be very, peeved at you. So.
Is the exam written?
Huh?
Is it written yet?
Yes. Yeah. Although Dr. Miller has made his changes. Yes. Yes, the exam is cumulative. I'm going to be covering all the topics that you will need for the exam, starting with a review of the first half. So these are a list of topics. By the way, all the slides will be posted online. Actually, they're already up online. And we will post a recording as well. Do you have a question? No? OK, cool. It should be. Yeah. If not, I'll just speak louder. OK. So first thing, these are the equations for complex numbers that you should know. This should be reviewed by now, but you have, this is in like the complex exponential form and conversion between the two. Sorry, this one. And you have the equations for cosine and sine. Note that sine you're dividing by 2i. Also finding the fundamental period, there's a strategy outlined here. You identify a single angular frequency omega for each of the sines or cosines or complex exponential terms in your signal. Use these equations to find out what your T0 or your fundamental period for a particular sine or cosine is. And then finally, you take the lowest common multiple of the fundamental periods to find the fundamental period for the entire signal. All right, so this is the first question we're going to go over, which is signal operations on the time domain. And you have three operations. You have time scaling, reflection, and time shifting. So for example, this is time shifting. So we have a signal S, and we're subtracting T0 by it. So does that mean, are we moving the signal S to the left or to the right? If T0 is positive. To the right, good. So let's do this example problem. This is your x of t, given this signal. It's like a trapezoid. And the question is, what is x of negative 1/2 of t plus 4? I'll give you guys like 1 or 2 minutes to draw the signal. There's a specific order you should use. OK. Actually, in the interest of time, I'll just show you guys the answer, and then I'll explain it. It looks like something like this. So we have a particular order of signal operations. So first thing is you use time shifting. It says time shifting b, but that's just the whatever constant you're using. You're shifting it by. In this case, it'd be you're time shifting it by 4 to the left. Then you reflect if the coefficient in front of your signal is negative, and then you finally scale it, where if it's greater than 1, you're compressing it, and if it's less than 1, you're stretching it. So how did I get that answer? Well, first thing to do is we're going to shift this by 4 to the left. So we're going to draw the signal. Plus 4. So because it's shifted to the left, so it'll be -1, 0, 1, 2. So this will look something like this. All right, this is t plus 4. Now we're going to do reflect. We're going to reflect it because it's negative. Oh, wait. This is not the same thing. Sorry, my bad. It's 35. So -4. Reflect it. All right. So this is -t plus 4. And finally, we scale it by 1/2, which means that we're going to stretch it by 1/2. So this, you're multiplying by 2 in this direction, so it'll become -2. And this, you're multiplying by 2 in the other direction, so it'll be 4. This is 1, so this will be 2. So it looks something like this. All right. Moving on, the next thing we're reviewing are system properties. So you have linearity, time invariance, causality, and memory. I'm not going to go through them right now because these are things we assume that you know from the past midterm. But if you do have any questions, come talk to us after this or during office hours. But these are the properties, and these are all from the notes, the tutorial notes. OK, so one thing we learned is that every system, if you send in the delta function, you get a special function output back, and we call that the impulse response. And with the impulse response, there's also a property which is called the sifting property, in that you can represent any function as a weighted sum of its partitions by the delta function. So in discrete time, it looks something like this. And continuous time, we have the integral version. Keep in mind, this is not the convolution integral because this is not the h of t or h of n. This is the delta function. Right. And from that sifting property, we can then derive the equations for convolution sums and convolution integrals. And someone asked us to do a graphical convolution example, and it may or may not show up on the test, so we're going to go over that one. And we're convolving these two signals to find the output. So we have x of t going from 0 to 1 with a height of 1. And you have h of t, t-axes going from 0 to 2 with a height of 2. Right. So we're asked to find the convolution to find the output, y of t. To do that, the general strategy is to pick one of the signals, actually take both signals and convert them to the tau axes, and pick one of the signals, reflect it vertically, vertical axes, and then slide it and look for regions where it overlaps. So in this example, we're going to be flipping and sliding x of t. So x of t minus tau looks like this. It'll be t minus 1 and t. And we have the corresponding h of tau, which is 0 to 2 still. Right. And now we consider cases. So first case, I'm going to go over here. Is our interval 1. We have t less than 0. So this is when there's no region overlap, right? So that means that y of t is just equal to 0 for t less than 0. Moving on to interval 2. We're going to consider this picture. Our h of tau still hasn't moved because we're only moving the x of t minus tau. Right. And our region overlap is this area between t and 0, between 0 and t. This is true when t minus 1 is less than 0, less than or equal to 0. Sorry, less than 0. And when t is greater than or equal to 0. You can see that t has to be greater than or equal to 0. And at the same time, t minus 1 has to be less than 0. And from these two inequalities, we get the condition on interval 1 that 0 has to be less than or equal to t, which is less than 1. And our y of t is an integral where we integrate over the region of overlap, or the domain of where they overlap, which is 0 and t, and their amplitudes. So x of t minus tau is 1, and h of tau is 2, and we take it over d tau. And this is equal to just 2t when 0 is less than t, less than 1. And then you continue with the next region, which looks something like this. 0, 2, t minus 1, and t. And this time the region overlap is between t minus 1 and t. And then your final interval, sorry, your fourth interval would look like this when your x t is like leaving the h of t. 2, 0. And finally, when there's no overlap again. So in total, you'll have 5 different intervals. And once you combine all of them, you'll get something, a y of t, that looks like this. 1, 2, 3. With a height of 2. And that's how you do graphical convolution. I'll skip the remaining calculations in the interest of time. But if you have other questions or want to review more, there's a graphical convolution worked out example under helpful links on course content. Right. OK, next topic that we want to review quickly is the differential equation difference equations. If any of these forms show up, if you can write it, the top differential equation difference equation in that form, then you automatically can say that the impulse response is what's given over here. So I would just use these directly. Keep in mind that your initial condition has to be y negative infinity equals 0 or y of negative 1 equal to 0. Final last thing we did in systems in the last exam was eigenfunctions. And they're basically defined as given an LTI system, if your input is the eigenfunction of the form e to the I 2 pi ft, then the output is the original eigenfunction times some h of f, where your h of f, as you've learned recently, is the frequency response, which is the Fourier transform of your impulse response. This slide is just to clarify notation we're going to be using. One is that I is the same as j. They're both imaginary numbers, different way of writing it. And angular frequency is different from regular frequency. Angular frequency is 2 pi f, whereas frequency just normal is just f. And f is, because f is 1 over the period, you can have that omega is also 2 pi over the period. And finally, this is the same thing when you're writing the frequency response. H of j omega is the same thing as h of f. All right.
Just like,
Yeah. Flip it on.
okay. Yeah, so we're going to use the notation 2 pi f. I think it's a little easier to do, a little more to write, but works out a little better with the math. So this is sort of visualizing the concept behind Fourier series. We want to represent this square signal as the combination of a bunch of imaginary sinusoidals. And the way we could do that is if we just have one imaginary sinusoidal, you know, it doesn't really get it, but we get the period in there. If we use another one at double the frequency, it gets a little closer. If we use another one and add that to it, it gets a little closer, and so on. So you can imagine if we keep on doing this to infinity, we would eventually get something that is the square signal. So that is Fourier series. And here's a nice little animation. So each of these is a different frequency, and these are your Fourier series coefficients. I could let it play through one more time if you guys want. Yeah? Okay. We'll let it run through one more time. But this is the Fourier series representation of that. All right? So we have our signal. This is in the time domain, the red one. All right? And each of these blue ones is one of our imaginary sinusoidals. Yeah. And then each of these is a coefficient value for that sinusoidal. So that's Fourier series. Yeah. Yeah, you can thank Victor for that. He found that animation. Yeah, pretty cool stuff. All right. Yeah, I hope that helped. Okay. So for Fourier series, it has to be absolutely integrable. That means if you integrate it from negative infinity to infinity, you don't want that to be unbounded. You don't want that to go to infinity. It has to be finite. And for Fourier series, it has to be periodic in the time domain. So this up here, this is your Fourier series equation. This is how you calculate your coefficients. And this one down here, this is your reverse or your inverse Fourier series, and this is how you calculate the time signal back from the coefficients. And notice that for Fourier series, it's periodic in the time domain, which means it's going to be discrete in the frequency domain. Any questions? Yeah. Yeah. So the animation, what it was signifying was, so basically, if this is our time signal, and we break that down into the summation of a bunch of imaginary sinusoidals represented by these blue ones, the blue lines that appear over here, that is the coefficient value. That's the magnitude, sort of, that these sinusoidals are being multiplied by.
The idea is like to increase the coefficient value to net sum, so it will eventually look like the time.
Right. Yeah, we just keep on adding new things until it does look like the time. Yeah. Yep. So this is an example of a Fourier series question that you might be expected to solve. Let's say we have a signal, and let's say for our cases it's all in sines and cosines, or something that's as equally easy to convert into imaginary sinusoidals. We know that the period of this guy is 1 and the period of this is 2, and that's shown here. So we take the least common multiple of those, and then we find that the period of the whole thing, this whole signal, is 2. Which means that the fundamental frequency is 1 over that, 1/2. All right? Yeah?
Why is it the least common multiple of 1/3?
That's a typo. Yeah, I modified this question while writing it. That should be a 2. I can fix that later. Yeah, 1 and 2. Ignore that. Yeah, if you guys see any other mistakes, just point it out. I wrote this late last night, so very possible. Lots of things wrong, but we'll go on. We use Euler's identity to convert cosine and sine into our imaginary sinusoidals, as shown here. That's just plugging it into the equation. And then what we're going to do here is we're going to represent each one of these guys in this form, where it's I 2 pi f naught, that should be kt. Okay? I 2 pi f naught k t, another typo. All right, so we do that here. So we have our coefficient e to the I 2 pi, this is k, 2, f naught is 1/2 t. All right, and I do that for each of these. Do you guys see how that's done? Are there any questions about that? That might be a little confusing. Okay, yeah, so, for example, this is I pi t. We know that we want it I 2 pi something 1/2 t, so that something's -2.
Wait, I'm sorry, you said the typo was an x of t, that should be I 2 pi.
I 2 pi k f naught t. Yeah. Yeah, and we'll fix these and re-upload them. No worries. So then what we can say is that we know that at a value of k equals 2, our coefficient is 1/2. At a value of k equals -2, also 1/2. Value of k equals 1, 1 over 2i. And at a value of k is -1, we got -1 over 2i. And then otherwise it's 0. All right? And that would be our final answer. That's the Fourier series representation. So that's how you would go about a problem that's made up of sines and cosines, something that you can easily convert with Euler's identity.
So why did you have to do that thing with the exponent if you were just taking the coefficient?
So what I'm trying to figure out here is what is the k value of this?
Okay.
Yeah. And the way I'm doing that is by writing this out in the form from the last slide. Any other questions? Yeah.
So the methodologies you solve for f naught, and then from that you make your x of t using the equation. And then from there you solve for the k values, and then from there you get the x of k values.
Yes, that is how you do it. Yeah. Any other questions? Okay. I think there are some more example problems like this in the TA notes that are online, so you could try those out in the homeworks too. It's a good process to know, definitely. Yeah.
So will solutions for the TA, like the tutorial notes, be posted or not?
I don't think so, although we do some of those problems in the tutorial sessions. So, yeah, and some of these are just really similar to those. All right, so let's say now we're in a situation where we don't have sines and cosines, right? Let's say we have a repeating square signal, sort of like in that animation, and now we want to get the Fourier series, all right? In this case, we can't just use Euler's identity and convert to imaginary sinusoidals because we need sines and cosines for that. So we're gonna actually use the equation. All right. So we know the period of this is 3, which you can see from the graph. So that means our f naught is 1/3. So we have our equation. We plug in 3 for t and 1/3 for f naught. Okay?
Okay.
Yeah.
I have a question. Why is t 3?
Yeah. So t is 3 because the period is where the signal repeats. So let's say we take here, where it starts to go up. The next time that repeats is at 2. So it's 1, 2, 3.
I guess I thought it was 2.
Should the 3s be 4s on the balance?
Where?
Middle one is 2 Ys and 2 X are 1.
Oh, that's crazy. So that -3 should be a -4.
Yeah.
Where is this?
On the graph.
On the graph.
The leftmost box is 1 unit.
Oh yeah, that should be 4. Yeah. Thanks. Yeah. So no, this still works. Yeah. Just imagine this is -4 and 4. Yeah. If you just imagine that's 4, -4. My bad. Any other questions? Yeah, -4 and 4. All right. So we have this, and we plug all our stuff in, right? And we're gonna for our period that we're integrating over, we could choose anything as long as it's 1 period long. So we're gonna go from here to here. All right. All right. From here to here. And notice within that range, our x, it's only 1. It's only a value of 1 from -1 to 1. Otherwise, it's 0. So our bounds go from -1 to 1 now. And we just say x of t is 1. And then we simply solve out our integral step by step. And we get to our final answer. Yeah.
Is it still the same thing as like the b sine of?
Right. Yeah, it's the same thing. This is simply the Fourier series version of
Do
it.
we have that on our chart where we need to do the derivation?
No, good point. Yeah, no. So right now I'm going to go through and I'm going to actually show you how to derive everything. But actually on the test, if you can use your chart or your properties, use them because it's going to be way faster and way easier. All right. Okay. Do you guys want to look at this more? Or? Okay. Yeah. Just remember this should be -4 and 4. But other than that, it should be all right. Yeah. Question.
So I think I asked this like in class a few days ago, but like when k is equal to 0, what is that like? In this case, this is just for k not equal to 0.
Mm-hmm.
What are you supposed to do when k does equal 0?
Okay. So when k equals to 0, what that means symbolically is that's going to be the imaginary sinusoidal that basically has no period. It's just a straight line. So that really ends up being, I guess it would be the mean of the signal, maybe. But yeah, if you plug in k equals to 0, this guy, I believe you use L'Hopital's rule from calculus to figure out what that would be. Yeah, it would be L'Hopital's rule, which might be from a while ago, but yeah.
Dr. Miller said that that's what it was. It's like the mean k equals 0.
Okay, yeah, I mean, yeah. Any other questions about Fourier series or solving it by the equation? I hear a lot of talking, so is there like a lot of confusion here, or is it? Yeah. Yeah.
They ask for the Fourier series, they're asking for like the trigonometric representation, but when they ask for like the Fourier series coefficients, they want piecewise functions.
So when they ask for either Fourier series coefficients or Fourier series representation, you could represent it either way. All right. In this case, you can't really represent it as a piecewise because you have like infinite of these guys. So that's why we just represent it as a function. But in this example, we represent it as piecewise simply because there's only like 4 instances that are non-zero. Yeah, so either representation is fine, whatever works easier. Yeah?
We have to specify what the value is for
Like in